James is actually a chief strategy and sales officer at ICE 3D. He's currently the business and strategy officer for ICE 3D Microelectronics, a fabless semiconductor company invested by ARM. And he also serves as a special assistant to the chairman of e-tron Technology. He is repeatedly invited to speak at effective presentations and has a track record of outstanding business leadership and success in consumer, machinery, and semiconductor companies. James has led the firm's corporate strategy and business planning and has secured numerous cases and opportunities. He also helped ICE 3D get investment from ARM IoT Fund, Y Harper, and other well-known investment companies. Thanks so much for presenting today. James, over to you.
Thank you, Aruna. Thanks everyone for coming in to listen to my talk. So my talk today is on sensor fusion on low power AI preprocessor. And the talk is going to be very applicational because the things that we're doing is kind of unique. So just giving you some background of what we're doing and who we are. i3D is a fabless company that does IC designs, but moreover, we actually do a lot of vertical integrations because when we first started, we were actually in the topic of stereo visions. At the time, stereo vision was not a very widely accepted or known technology, or not an easy technology to be implemented or to be produced. So we took our IC and started making systems, stereo cameras to be precisely, and then upon that, we started building software as well as system layers on top of these chip that we do. Generally, we are a silicon carrying SI company that help our customer to save cost and development while they're developing their cutting edge computer vision technologies and products. We are invested by ARM IoT Fund as well as a few known ventures in the world. And we're partnering with a lot of the big companies in the world to carry out solutions based on silicons. So before I begin in talking about sensor fusion and the things that we're doing, first we gotta talk about what sensor fusion is. So basically, it's a sequence of observations from multiple sensors or one sensors, and usually real time. And then we use that with filters as well as processes to better estimate the known quantity of something or objects or target state of position, and associate that with some of the uncertainty measures at a given instance. But to do this, it's actually quite difficult because a lot of people talking about sensor fusion initially, they were just thinking that, hey, we're just combining a bunch of sensor and timestamp it together, throw it to the back and let the SoC handles it. But then that is not considering a few things. First is the environment. And second, when you're carrying out such behaviors in the lab, it's usually at a control scenario, and then the environment is more predictable and it's more controlled, whereas the actual environment is very complex and unpredictable. And lastly, taking the sensor fusion data into real applications is actually not as simple as we thought, because for each of the products or each of the development that we're doing, for example, the latest hot topic has been on the autonomous vehicles. When do we take what data and what level of process data being used in the actual behavior of the systems all varies. And right now, we're looking into specifically the realm of robotics, where it's very diverse and then they do a lot of different things. Therefore, the things that they need, the data that they need, and the behavior that they do is more unpredictable. So putting it into a more integrated way and also more cost-effective way is our topic and our target. So we spun off from a listed company in Taiwan. It's actually a memory company. So I feel attached to what we was sharing earlier. Since then, since 2016, we spun off. We sold millions of chips to a lot of the very, very big companies in the world. We're one of the first suppliers to Oculus, as well as Amazon in their Amazon Go store that I can share because it was public. And throughout the past 6 years, we've been focusing a lot of developments on AR/VRs, as well as AMRs, robotics, as well as AIoT, some of the emerging blue ocean markets. Most of the customers that we're working with are Fortune 500 companies. We have about 10 NP projects to deploy to the market in the past 6 years, and then numerous development ongoing. Today, before I go into dive into the chip session, I really want to cut into the topic by sharing some of the applications that we're doing, and then really to analyze on how each of these applications requires in terms of sensor fusion applicational situation. So first, I'm going to start talking about one of the hot topic now as well. It's regarding the AR, VR, and XR devices. So this has become a very popular because of what Meta is investing in, and also with all the cloud infrastructure as well as connectivities catching up with the processors. It's expected that these devices will play a big role in the future commercial product area. But each of these devices requires differently in terms of the sensing as well as compute, more importantly, the power when they're in actions and operating. So in the case of AR glasses, silicons, so basically you want a real high energy efficiency and a very small form factor while maintaining the ability to do audio sensing as well as interactions, computer visions with 2D and 3D in ways of AI implemented with segmentation. And usually in this kind of scenario, we're talking about an SoC design that not only does sensor fusion, but as well as carrying OS to carry out some of the applications as well as the UI UX. So we're talking about very integrated designs. So nowadays, I think no matter what we're talking about, but specifically for AR glasses, energy is definitely something that we take account to the most. If we compare moving data and computing data, we can quickly realize that actually moving data between memories is very highly energy inefficient. So that's something that we're watching out for. One of the recent development that most of the chip providers or IC designers are doing into is that they're taking these NAND accelerators, rather than putting them on the system bus, they started combining them with a lot of the signal processing IPs. For example, the speech IPs as well as the vision IP, having them closely bind together, reduce the redundancy of moving these data through the AXI bus, and utilizing the CPU, less utilization of the CPU as well as the system memory. The other thing has always been talking about, there's still a need that we have to move data, but then how can we increase the quality of the data that we send out for further process? In this scenario is to the cloud. So basically what we want to do at a preprocessor is that we want to make sure that we can condense the signal in a few approaches. One is to denoise. One is to get a selection down to a numerous result for the NLUs at the cloud to better compute the data. And then the other thing that is being talked about is obviously reducing the bit efficiency to save power, and then use quantization aware training to enable better result for the low point scenarios. Give me some examples of what a lot of people are doing. So this is a development by obviously Microsoft, the famous HoloLens. So the approach that I use to design their IC is by putting a lot of these vector processors and then a lot of these proprietary engines, accelerators to do application-specific work for AR glasses. But there are some trade-offs when you do design like this. Usually these kind of ASIC are only for single product and single purpose use. Therefore, if the product and the development does not come to a certain volume, the economic effect is not very good, because basically you're spending a lot of money but not selling enough. So just keeping that, I'm jumping into the next topic where I was talking about in terms of the AMR development. The most widely known AMRs are definitely the autonomous vehicles, but there are so many things that can classify as AMRs. There are service robots where they carry your food from the counter to your table, and there are bin picking robots, there are constructional robots, there are cobots that does pick and place, all sorts of robots. So earlier when I was mentioning making ASICs for AR, VR, combining all those sensor fusion engines together with a CPU or an OS processor, that probably will not work here for a few obvious reasons. One is because the form factor varies. So you might have sensors flying around very, very far away from each other. That's number one. Secondly, is that you might need more sensors in this scenario than the other scenario I was mentioning in the AI VR scenario. So basically, how to design a chip with good flexibility is very important. That's what we're doing. Moreover, I think to bring that development into products, you need to be able to be aware that what is essential and what is value added. So what we're doing at i3D is that we built a platform, obviously based on the silicon, not just selling you the IC, but integrating all the softwares as well as the algorithmics that's required for the basic fundamental needs of a robot AMR. So basically everything will have to move. But on top of that, as for how the sensors are being integrated and fused, that can come in a flexible way, which I will talk about later. So nowadays, when we talk to sensors, there's whole sorts of sensors around. So you have 2D sensors, 3D sensors. You have all acoustic sensors as well as millimeter waves. And then, although a lot of these sensor data are being put into a lot of the AI and deep learning works, right now, still the CMOS-based RGB sensing data are being is the most advanced development. So how can we shrink that, providing a more integrated service by not only offering chip, but as well as algorithmic solutions is what we've been doing. So I want to make a few examples of what we've done throughout the past 1 year or two. So basically the scenario that we have right now is on these autonomous cards. All these cards will need a few things. First, they probably need to have a good ability to do scene understanding. They need to do SLAM. They need to localize themselves. But bringing the cost down is one of our topics. So taking the optical system and using algorithm and then ASICs to develop a result that is better than using expensive sensors such as LiDAR is our target. A few things that is required to do that. One is the noise. So basically to get a good data, try to do denoising at a preprocess is important. And that can come in a few different ways. The conventional way is by implementing a digital ISP pipeline, but then it's being very popular by implementing light-weighted AI models to do better denoise and flexible denoising on different scenarios. Secondly is, since we were doing stereo vision, I want to take stereo vision as an example. So taking the denoise images and do more innovations on the data processing pipeline is also what we've been doing. So on the right, you see a depth information is actually being generated by a pair of stereo camera as well as a fisheye RGB camera. So basically what we do is that we take the stereo depths to generate a binary object mask, but then we also use the RGB fisheye camera to generate a monocular depth estimation. And then we combine the relative depths together with the object depths to create a scale map. And we use that scale map and then using the number of scalings and divided by the number of DGC layers to get a more absolute depth out of these data relevantly. Because for stereo depths, you can get a very good accuracy and performances in close ranges, but at far distances, actually it goes into scenarios where it cannot see because of the limitation of the sensors and the weather scenario. Whereas the RGB monocular depth estimation does not do a very good job at estimating the very, very accurate Z distance, but it does a very good job of interpolating as well as predicting the distances after you have a ground truth. So we here use the stereo depth as a ground truth and use the RGB monocular depth estimation to enhance it. As a result, we actually developed a very interesting network called a tri-SD-net. So basically the backbone of the tri-SD-net is a combination of dense map as well as hardnet. So what we do is actually we take the, We actually take the step of doing downsample and then upsample it again, and we try to remove excess pooling as much as possible to make sure that we have the least amount of memory access, therefore also increase the real-time ability of the process. So in doing that, we can get a very, very good result of not only the SLAM feature point extractions obviously contribute to SLAM, but it also contributes to what we're seeing right here is the scene understanding in terms of recognizing the ground if it's accessible. So here on the different scenarios, you will see that using the RGBD as well as the sensor fusion approach together with AI, we're able to see what is accessible by the AMRs, what is not, and the distance information as well as the slope information of each of these accessible and inaccessible areas where the AMR is trying to reach. So this will be a very good example of sensor fusion. And at the top, we're combining IR images together to make sure that we don't get a false result when we go into a strong light or a very dark condition. I want to mention a work that's being carried out at the University of Ottawa. So they have a very good idea of interpreting the fusions, putting into different stages, early, late, as well as mid levels. So early fusions is what we are very, very familiar with, just combining the two different sensor and then interpolate it into many different kind of data and results. Second is adding recognition and understanding data on top of certain type of generated sensing images. Ultimately, combining all those results, we hope to get a temporal recognition out of the images rather than just, knowing that, hey, there's certain people, how many people are in the images. Rather, we are supposed to know, for example, where my mouse is pointing at, this is a baseball game occurring, not just two people in the grass and then maybe a ball flying. That's not what we want to get. So that's also a very important element when we're considering sensor fusion. The whole process of sensor fusion in a block of system, you will have the data generation as well as the signal process being done actually by a digital block or accelerator. And then further, you will do the noise and filtering and quantization and level filtering, and then having its timestamp and sync. But this approach does not always have to go with the same flow. So basically having a flexible design and having able to adapt the different type of pipeline in terms of processing these kind of sensor fusion processes is very important, because there are so many things that could happen in a sensor fusion process when you're talking about application together. So that's why when NPU comes in. So this is a very good chart that's being done by ARM as well as NXP. So they threw out a very good chart in explaining what level of NPU requires, what level of application requires what level of NPUs. Obviously, at this case, without considering too much of a throughput. But then we do see the value of these NPUs carrying out these AI algorithms and AI models. Obviously, they're a lot better than CPUs. Most of the development right now are separated by the type of CPU and NPU you use, and this is where we do things differently. So we think that right now, as you probably a lot of you know, like about semiconductor, stacking dies is very important. So for a lot of the scenarios and applications, you don't really need to have a very high performance NPU and CPUs, but there are some scenarios where you will need high performance NPU and CPUs. So how do we combine that? Is obviously what I just said, is by stacking dies together. So our development is by having separate development on these IC dies, by separating the functions of these dies and having them into different processes. Here I separate them into two parts. One is computing, one is peripherals. So peripherals are usually the receptor, so the receptor of the sensors. So they carry a lot of MIPI inputs, a lot of sensor inputs, and usually carry a lot of different signal processing as well as accelerators. Whereas the C portion carries mostly NPU and CPUs. So this way, doing ICs this way can give us a lot more flexibility. For example, if you were to have a vehicle or a product that requires 20 sensors, you can simply make a chip or package a chip based on two P chips together with the same C. Because what we observe is that in the recent development or the current development, a lot of the CPUs and the NPUs, the base level are the same. So a certain product usually requires some level of computation as well as the AI abilities. It's only wise to have that computing unit being built separately. Therefore, in this scenario, you can imagine if we need more CPU and NPU powers, we can simply stack more C chips on top of these P chips. And also they can be used separately as well. For if for your application, you don't need a lot of sensor inputs, you only need to have this NPU and CPU together. We can have the CPU provided to our customer in development solely without stacking them together. But if you would need a lot more sensor inputs as well as these accelerator engines, you could simply stack a C on top of the P chips to get a more variety of functions. So that saves us, the IC design house, a lot of time for development as well as our customer as well. So we can make a customized chip for our customer very fast by stacking dice together. This is an example of what we can do. So basically in these scenarios, we have 3 dies. You can imagine die number 1 is a C chip. So it's able to do high-level inference. It's able to do the level filtering as well as time sync and stamp, and then run applications such as SLAM on the CPU because it has a larger CPU cores. And then for the die number 2 and die number 3, you have micro NPUs, usually more than one micro NPUs, and micro CPUs such as the M55 or M35 CPUs that ARM carries, as well as what we call the XPUs. These are generally the accelerators as well as the signal processors that we have in. And we'll use these die number 2 and number 3 to do the filtering and denoising and the signal process before going into the host processors. But then host processor in these scenarios, they're all packaged in the same chips. So you can actually consider this as a SoC. So lastly, just before I wrap up my session, in Taiwan, we find it's very difficult to carry on a very good product development without software support, and that is very lacking right now in Taiwan. So for any of you who are in software IP development, like we really want to talk to you and talk more with you because we have a lot of projects that require a lot of softwares. So this concludes my sessions. Thank you.
Thanks for sharing some very interesting applications, James. It's awesome to see the number of applications growing in the space.
Good. Once again, we want to thank our sponsors, Tiny Edge Impulse, one of the leading what's called platforms for Edge ML and using tinyML applications. Our executive sponsors, Qualcomm, who have advanced AI research to making efficient AI ubiquitous, both hardware and software. Cintiat, accelerating your edge compute. Platinum sponsors, DeepLight, fastest video analytics solutions on ARM CPUs. Kilkatech, global IoT solutions. Renesas, basically big ideas for every space. The Sony Semiconductor Solutions Corporation. Gold sponsors, Analog Devices. ARM, who also have their own talks, so please feel free to sponsor them and jump onto their line as well. PhotoHub, making over-the-air firmware and model updates simple and accessible. That's probably one of the key things moving forward, so have a look at PhotoHub. Microsoft, for their edge capabilities and technologies, including all their, Azure services to support tinyML. NXP, together accelerating breakthroughs that advance our world, a great hardware provider. SensiML, analytics toolkit suite to be able to do your AutoML capabilities. STM Microelectronics to provide extensive solutions to make machine learning easy. Synaptics, engineering exceptional experiences. And then a list of silver sponsors, including AIZip, Aeon Devices, EMSA, Greenwave Technologies, Gravity Inc., IBM, Imagimob, Etermis, Nota AI, OctoML, Prophecy, Quexo, Rexon, SAP, Silicon Labs, Stream Analyze, TDK and Vincent. So thank you once again for attending. I hope to see you tomorrow online to listen to some of those interesting presentations. And thanks to everyone. See you soon.